Hi everyone, this is Jiao. In this video nugget, I will introduce you a high-power, high-frequency, 3-level neutral point clamp power conversion system for the renewable energy and nanogrid applications. First, let me briefly review the system structure. This is a two-stage power conversion system. It contains a DC-AC converter and a DC-DC chopper. The AC side is connected to a 480 volt or 600 volt utility grid, and the DC side can be connected to 400 to 800 volt DC bus. The AC and DC side is decoupled by this 1200 volt DC link. The whole system has 200 kVA power rating with 20 kHz switching frequency. It has a bidirectional power flow with 4-quadrant operation capability. This power conversion system can serve as grid interface for renewable energy or energy storage system. It can also work as a power supply for various loads or drive motors in industrial or transportation applications. The whole system has a modularized structure and over 98.5% efficiency with very high power and high frequency. The modularized face-like building block uses 3 layers of laminated bus bar as 3-level rail to reduce the parasitic. But the parasitics in switch modules and inner connections still results in 2 different switching loops. The short loop contains 2 modules and 1 connections, while the long loop contains 4 modules and 3 connections. The 4-quadrant switching loops for DMPC varies with power factor. To avoid the long switching loop with large parasitics, conventional AMPC face-lag can be used with only short switching loops. To further improve the switching performance, I proposed a new switching mode for AMPC. The 4-quadrant switching loops use paralleled long loop and short loop to reduce the commutation current. This proposed method has reduced switching stress and loss. The maximum switching stress for each device in the face-lag is measured for different modulation scheme. The proposed method has lower voltage and current stress compared with the DMPC and conventional AMPC. Moreover, the switching stress is distributed more evenly among all the devices. The face-lag loss distribution is also compared for the conventional and proposed AMPC modulation. The result shows that the proposed method has more evenly distributed loss for each switch. And finally, the total system loss for the converter is compared for conventional and proposed AMPC modulation. The proposed method has largely reduced conduction loss because of the paralleled neutral current path. As a result, the efficiency for the whole system is up to 98.5%. This is the modularized face-like building block. It uses a 1200 volt 400 amps single IGBT module. The gate drivers are customized for switching performance optimizations. They are interfaced with the control card by these optical fibers and this gate interface board. Here is the 3-level NPC power conversion system hardware. The left-hand side of the cabinet contains the DC-AC inverter, and the right-hand side is the DC-DC chopper. The modularized face-like building blocks are mounted on the top part of the cabinet, and the auxiliary circuit and also some passive filters are mounted at the bottom of this cabinet, and the control card is mounted at the back of this cabinet. The DC-AC power stage contains 3 of these face-like building blocks and a customized LCL filters. There is a passive damping circuit for the filters, which has a very low loss. The common mode chokes are placed at both inverter side and the grid side. There are also pre-charged circuits, sensor board, and also fuses as the auxiliary circuit for the DC-AC part. The layout for the DC-DC power stage is similar to that of the DC-AC part. The integrated coupled inductor for the DC output is a very novel design to reduce the volume of the passive components. The common mode choke at the DC side suppresses the leakage current and avoids large transformers. There are also a pre-charged circuit at the DC side to establish the DC link voltage from the DC side. The whole power conversion system is controlled by a modularized digital controller system, which is mounted at the back of this cabinet. This is the control card with an DSP and an AD chip. And this part is the modularized signal conditioning system. There are also some flexibly configured plug-in board for digital signal input, signal output, and also display. And this is the Ethernet card for human-machine interface. And there are some modularized gate driver interface board for the DC-AC and DC-DC part. Then I will show some experimental waveform for the power conversion system. First shown here is the test result for the DC-AC part. The converter is running at closed-loop rectifier mode. The output current and DC-link voltage is controlled. This green-colored waveform is the line-to-line voltage waveform, and the three other sinusoidal waveforms are the grid current waveform. This waveform shows the test result of the DC-DC part. It is running at an interleaved buck mode. The phase-lag output voltage is in the green color. It is a 3-level output voltage. And these are the two-phase inductor current in the coupled inductor. They contain both common mode and differential mode components. And this yellow waveform is the total output current waveform of the inductor. This screen shows the human-machine interface, which is used to control the system and display the system variables. The start command can be set to the two stages separately, and the system running status, like PLL and contactor status, are indicated in this human-machine interface. The key variables of the converter, like the grid voltage, grid current, DC-link voltage, active and reactive power, and DC set voltage and current, are also displayed by this human-machine interface. So that's all for my video nugget. Thank you for your watching.